Hi everyone. Today we are going to discuss about OTTO cycle. There are 1, 2, 3, 4, 5 questions. Sorry for the silly mistake. So for the question 1, we are not going to discuss today. Definitely you can practice it by yourself by referring to some reference or the YouTube and my lecture notes. Okay, so question number 2, we move to question number 2. The question given that the OTTO cycle has a diameter of 20 centimeter and the stroke length of 45 centimeter. If you refer to the definition of stroke length, it's the stroke, the piston can move, can reach, okay? So means that it won't reach to the clearance volume. So the place that it could reach is exclusive the clearance volume, okay? So then I draw it out, okay? My my stroke length is 45, just below the VC, and the diameter is 20 centimeter. Okay, so the question asking whether it's above 60% efficiency. And we look at this diagram. If you look at the notes, there is one similar one. And if you actually, I just turn the cylinder to 90 degrees. And you can see that the V1 is the stroke length plus the volume of the clearance volume. And V2 is the clearance, right? Does that make sense? Okay, so in order to check the efficiency, we need the RV. So we need to find the RV first. We know that RV is equals to V1 over V2. And V1 is Vs plus the stroke volume plus the clearance volume. So the stroke volume is given all the information, you can get it. So then you just plug in all the value inside this formula, you're able to find your RV and plug into this simple efficiency equation, you manage to answer the question number 2. So next move to question number 3. In an air standard OTTO cycle, the compression ratio is 6 and the compression begins at 1 bar and 232 Kelvin. The energy supply to engine is 2,510 kilojoule over kg. Determine the maximum temperature and pressure of the cycle. Well, first thing is we extract all the useful information. Given is RV is 6, P11, T1 is 323. The Q in, this is small q because it's over kg. Okay, so maximum temperature, if you are the beginner, you are not familiar, I will advise you to draw the PV and TS diagram. So for the OTTO cycle, first 1 to 2 is isentropic compression. So isentropic compression is no work in, energy in or out. So entropy is 0. So therefore you have a vertical line from T1 to T2. The temperature is increasing because you're compressing it, but there's no energy. And then 2 to 3 is sparkling, Q in, so heating. So at this part is constant volume, heating, okay? So since the volume is fixed, but the pressure increasing, definitely the temperature increasing as well, and so as the entropy. 3 to 4 is isentropic expansion. Isentropic expansion is no Q in, no entropy. So you have the vertical going down from V3 to V4. Can you see that? Here. And then cooling, okay, constant volume, back to the original place, right? And therefore you have this PV and TS diagram. So first we find the given information mostly is we start from 1 to 2. So we know that is isentropic, we can use this equation. And if you look properly, the RV is V1 over V2, but this is V2 over V1. And indirectly, this is 1 over RV. And then after that, plug in all the information out, and then you can get your T2 here. Where's my T2? T2 here. Okay. And then we also can find the relationship between P1 V1 power of gamma equals to P2 V2 power of gamma, because this is isentropic adiabatic. So we have the, yes, we have the P1. We have the P1. Okay, the P1 is given. Where's my diagram? We have the P1 is 1. We can use 1 over 6 for the V2 over V1. And and this is 1.4. And therefore, you can get your P2. Check the value, but I am sure that my step is correct, okay? And then after that, then we can, since we have the T2 and P2, we move to 2 to 3. So 2510 equals to CV T3 minus T2. Okay, so we know that T3 is bigger than T2. So this equation is correct. So we plug in all the information inside, we're able to find our T3, right? So we know that this is constant volume at 2 to 3. So we use the perfect gas equation. So we can cut off the V, right? So then we can have the P3 equals to P2 over T2 times T3, okay? And since we have the P2, we have the T3, we have the T2, so we're able to find our P3, and therefore the first one is achieved. Okay, so we found our T3 and T2. Number B is the work done. Work done is Q in minus Q out. We are given Q in, 2510. We need to find the Q out. Okay, so in order to find the Q out, where is Q out? Q out is over here. Q out, 4 to 1. Okay, so means that we have to step by step, 2 to 3, 3 to 4. Step by step to achieve, to reach that. Okay, so continue, 3 to 4, isentropic expansion. So since we have the, we use the isentropic equation, since we have the T3, and we know that V3 over V4, actually the length here, they are the same, right? It's common sense, it's in the piston. So then we just plug it in, and then we're able to find our T4. So your question is, where is your work done? Right, I forgot to write it out, but it's quite simple enough. So the work done is actually, and I just write it here, okay? Probably I use work done equals to, sorry, the Q out. CV T4 minus T1. So since we have the T1, but we don't have the T4, right? Therefore, we need to find the T4. So just now from this equation, we find the T4, we just plug it in, we're able to find the T out, the Q out. So since you have the Q out, so you minus, given is Q in is 2510, you minus the Q out. Your work done is 772 kilojoule over kg. Okay, you can check it out and get back to me if you couldn't get the close answer. So then you have done the B part. What about the C part? The C part is efficiency. The efficiency, since you have the compressor ratio, plug it everything, you're able to achieve the efficiency value. So we move to D. D is the mean effective pressure. Mean effective pressure is the work done over the stroke volume. So we have done find the work done, which is Q in minus Q out. Okay, and then we need to over the V1 minus V2, but we don't have V1. So what we can do is we can use P1, V1 equals to MRT. So since this is per kg, we can assume this is 1, okay? So we have the P1, we have the R, we have the T, okay? So this is assumed equals to 1. So definitely we can get our V1 is 0.9. And don't forget that RV equals to V1 over V2. So very easily we can find our V2. Plug it in and simplify it. And then you can get your MEP for the question 3. Okay, so we move to question number 3B. The quantity control engineer would like to test the performance of new OTTO cycle engine. The hot air is 70. So T1 equals to 70 plus 293 Kelvin. And the pressure is 1 bar. The P2 is 7 bar. So why? It's compressed reversibly adiabatic to 7 bar. So it's from 1 to 2 is P2 is equals to 7 bar. And 500 heat is added. So the Q in is 500. Could you please help him to determine the compression ratio of the engine? So, well, this is quite straightforward because we have the P1, we have the P2. So, and then we also, do we have the RV? So we don't have the RV, but we have the P. We have the P1 and P2 by using this equation, right? So we can just plug it in, okay? Rearrange again, and we can use the P2 over P1, this formula, we can get our RV, okay? B, the temperature of the compressed air before leaving the compressor. So the temperature at the end of the compression. So if you look at this graph, the temperature before leaving the compressor. So it's T2, right? So once you leave, the T2 is going to heat in. Okay, so it's isentropic again. So we can use this isentropic formula, plug it in, and then you can find the since you have the T1, right? So then you're able to find the T2. You have the RV. Okay, you have the RV. You have this gamma. Okay, now you're looking for the T2. So you're able to find your T2. Okay, number C, the temperature of the air at the end of the constant volume compression. So it's obviously, if you look at this, at the end of the constant volume Q in. So we know that we need to look for the T3, which is the maximum temperature. So Q in is given, right? And then the T2, we found it from here, which is 604. Oops, I shouldn't let you know the answer, but you know, so you can check it out later. So by plugging out everything, you're able to find the T3 equals to 1311. Number 4, okay, which is actually number 5. The OTTO cycle engine has a clearance volume of 500 milliliter and the stroke volume of 6 liter. The inlet pressure and the temperature are 1 bar and 20 Celsius respectively. The pressure at the end of the heat added is 20 bar. Determine the maximum temperature of the cycle. If you look at this, we extract the information first. Okay, the VC is 0.5, the VS is 0.6. Okay, and the P1 is 1 bar, the T2 is 293 Kelvin, P3 is 20 bar. Okay, still again, we are looking for the maximum temperature. So T3. And the thermal efficiency. So the thermal efficiency, you need to find the compression ratio. So 1 to 2, in order to get the T3, you need to step by step from T1 to T2, T2 to T3. So 1 to 2 is isentropic. Use the isentropic equation. So since we have the T1, we can use V1 over V2. How to get this is, since we know the VC, we know the VS, we can use this formula, okay, to find our RV. So once we have our RV, then we can use the RV into to plug in here, okay? So, and then we able to find the T2. Okay, P1 V1 power of gamma equals to P2 V2 power of gamma. So then we rearrange again, and we can find that V1 over V2 power of gamma equals to P2 over, because the P1 is equals to 1. So, and it's very easily you can find your P2. Okay, so 2 to 3 is constant volume. Since the constant volume, we can use the perfect gas condition. We cut the volume out. So since you have your P2 just now, you have your T2, okay, which is here, your T2, and your P2 is here, and you can find your P3. So plug it in, you're able to find your T3. Your your P3, sorry. Let me erase this part. Okay, so the P3 is given here. Okay, the P3 is given here, and therefore, we can have the T3 value. We can get the T3 value. So, and then next is the efficiency. So once we have the efficiency, and then we can achieve on, we put in the compression ratio, we're able to find our value for the thermal efficiency. So if you look at this one, very easily, you can notice that there are a lot of terms on efficiency for the OTTO cycle, and again, it's just play around with the temperature, play around with the work done to find the efficiency. So it's a quick revision, discussion on the tutorial. So I hope you are clear on this one. If you have question, please send me a message, leave me a message later on this part. Thank you everyone, bye.